We are really going back to the basics today. And in fact, if you've had any of this in physics or in your profession, you're probably just going to be bored with this particular lesson. But if you haven't had a lot of experience with current, resistance, and voltage, this might be a good lesson for you to hang out with. We're going to be talking about two laws today. We're going to be talking about Kirchhoff and his voltage law. And we're going to be talking about Kirchhoff and his current law. Now, these both have this idea of conservation of, well, energy. Think about going around your neighborhood in a bicycle. When you leave your front door, right, and go throughout the neighborhood, if you've got a hilly neighborhood like mine, you go up hills and down hills and up hills and down hills. Up hills, kind of like resistance. Down hills, kind of like a source, provides you with energy. All the way throughout the neighborhood, when you get back to your house, you've gone up exactly as much as you've gone down. And that is kind of what these Kirchhoff's current law and Kirchhoff's voltage law are talking about. We are going to go up as much as we go down, specifically when we're talking about the voltage law. In fact, let's draw a quick circuit here. The type of circuit we're going to draw here is something referred to as a series circuit. Now, a series circuit means that all of our devices are in series. The end of one is connected to the beginning of another. And I'm going to do a really easy circuit here. We're going to take a battery, and we're connecting it to 1, 2, 3 resistors. All right. Now, the value that is, well, one of the things that we have to understand is that if an electron leaves this negative terminal and flows through this resistor, it has to also flow through that resistor. It has to also flow through that resistor to get back to the beginning. In other words, every little bit of current that leaves the positive side of our circuit here, every bit of that current I has to flow through all through those three of those resistors before coming back to the end of the battery, to the negative side of the battery. Now, we're going to go ahead and I'm going to make up some resistance values here. How about we have, and let's get back to this idea of the bicycle going through the neighborhood. As I go, so coming out of the battery here, I'm at kind of at the bottom of the hill. The current, the potential, the strength that I've got is going to have to drop as I go through each one of these resistors. So I have this potential, I have all this potential energy, I'm high up, but as I'm going down, I'm losing some of that potential. Keep losing some of that potential. So each time I go through one of these resistors, I lose a little bit of potential until I've gotten back to exactly the same, the zero reference that is on that negative side of that battery. So let's just come up with some resistance values here. How about 3 ohms? How about 2 ohms? And how about 1 ohms? All right. Now, these voltages that I've got, I'm just going to label them V1, V2, and V3. All right. Now, what Kirchhoff's voltage law says is that the voltage that's coming out of that battery right there is equal to V3 plus V2 plus V1. Let's go ahead and just pick 12 volts here as our voltage for our battery. That means that 12 volts is equal to V1 plus V2 plus V3, right? As we go around that loop, the series circuit. What do V1 and V2 and V3 equal? Well, remember Ohm's law from last time. Ohm's law, we started out by saying that Ohm's law, current is directly proportional to voltage, but inversely proportional to resistance. You modify that expression a little by moving resistance to the other side of the equation. Another way of saying that is voltage is equal to I times R. All right? So what does that look like when we come over to our circuit here, our expression over here? Well, that says that 12 volts is equal to, well, V1 is equal to, remember the current has to flow, the same current is flowing through all three of those resistors. So that's V1 is equal to I times 1 ohm plus I times 2 ohms plus I times 3 ohms. All right. Well, if we pull an I out of that, we get I times 1 ohm plus 2 ohms plus 3 ohms. All right. Kind of looks like that, doesn't it? Looks like that, where our voltage, 12 volts, is equal to simply I times, what, 1 plus 2 plus 3, or 6 ohms, which means, well, we resolve this so that we have I is equal to voltage over resistance. I is just equal to 12 volts over 6 ohms, which is equal to 2 amps. All right. Now, the important thing here is to see that the 12 volts sees, the 12 volt battery sees a 6 ohm resistor as far as it's concerned, which is just the sum of those resistances. But what are each one of these voltages? What's V1, V2, and V3? Well, we already know that the expressions are just simply the current, now that we have the current, times the resistance. So it'd be 2 times 1 equals, so the voltage across this first one, we've got 2 amps times 1 ohm, that's 2 volts. So V1 is 2 volts. V2 is equal to 2 amps times 2 ohms, which is 4 volts. V3 is equal to 2 amps times 3 ohms, which is 6 volts. So what do we have as we're going around here? Well, as we're coming around here, we go 6 volts. So we took 6 volts away from the 12 volts. There's only 6 volts left right there. As we're coming across the 2 ohm resistor, V2 is equal to 4 volts. You take 4 volts away from 6 volts, we have 2 volts left. And as we go across this last resistor right here, we have 2 volt drop across that resistor. That brings us to 0 volts. And so we've gone from the 12 all the way back to the 0. All right, now we'll talk about voltage dividers. This is basically a voltage divider, and we'll talk about the importance of voltage dividers in the next lesson when it comes to accessing the external devices such as a joystick or a push button whenever we're trying to connect that to our processor. Now let's talk about Kirchhoff's current law. Kirchhoff's current law says that if you have a current coming into, and I'm going to temporarily draw something here. If I have a current coming in to, and this guy right here is called a node, then the current that comes out, we'll just say I1 and I2. So the I total is equal to the current I1 plus I2. Let me try that a little bit differently, because that's not quite what Kirchhoff's current law says. Kirchhoff's current law says that the sum of the currents coming into the node are equal to the sum of currents going out of a node. And that's really kind of what I'm saying here. What I've got is, if I've got a current coming into a node that branches out, the currents that, some of the electrons are going to go north, some of the electrons are going to go south. But we ain't going to create any new electrons, and we're not going to have any electrons disappear. So the total number of amount of current going into a node is equal to the amount of current coming out of that node. So let's draw another circuit. This one's going to kind of look a little different. In fact, this circuit is what we're going to call a parallel circuit. Now, a parallel circuit, if I have that same 12 volt battery, but this time it doesn't pass through the resistors in series, it passes through the resistors in parallel. Now, by having these resistors in parallel, what that means is the current coming out of the positive side of the battery, the current coming out of here it has to make a decision at that node. Some of it's going to go through the first resistor, some of it's going to go through the second resistor. Now, the key is about this particular drawing here is that it's important, well, it's important to note that the 12 volts that comes out of that battery, remember, we're looking at Kirchhoff's voltage law, which says that the voltage drop as we come from this node right here to this node right here, it has to be, if this was in a black box, the drop from that node to that node has to be exactly the same as the voltage that's across that battery. So what we have here, in this case, is that 12 volts is across both of those resistors. All right, well, let's make a couple of resistors. In fact, let's go ahead and let's make one of these resistors 24 ohms, and one of these resistors 8 ohms. All right, so that means that we don't necessarily know the total I yet, but we do know we can figure out the current that goes through each one of those branches. So first of all, let's take a look at the current going through the 24 ohm resistor. Well, if we come back up to Ohm's law, it says that the current is equal to the voltage divided by the resistance. So what we have is 12 volts divided by 24 ohms, which is equal to 0.5 amps. All right. Now what about the current going through this other resistor, the 8 ohm resistor? Well, I8 is equal to 12 volts divided by 8 ohms, which is equal to 1.5 amps. So that means I have half an amp going through the 24 ohm resistor. I have 1.5 amps going through the 8 ohm resistor. What does that give us in terms of the total current? Well, the I coming out of the battery is going to equal, because of Kirchhoff's current law, 0.5 amps plus 1.5 amps, which is equal to 2 amps. Now, if we have kind of considered these two resistors to be in a black box, what does it look like? What is the effective resistance that the 12 volts battery sees? Well, we go back to actually, we go to the third version of Ohm's law, which says that resistance is equal to voltage divided by current. All right. And so as far as the 12 volt battery is concerned, what it sees, this effective resistance is equal to, well, we have the voltage, 12 volts divided by 2 amps. The effective resistance is 6 ohms. All right. Kind of crowded up a little bit too much in my board here, didn't I? Now, what this tells us, and the reason why this is of importance is because whenever you look at the resistance, the effective resistance of resistors in parallel, notice this guy's 24 ohms, this guy's 8 ohms, the effective resistance was 6 ohms, less than either one of them by themselves. The expression used for this, and we use a similar process when we figured out what the effective resistance of a series circuit was. Whenever we look at the effective resistance for a parallel circuit, so this is for parallel, all right, the effective resistance, 1 over the effective resistance, is equal to 1 over R1 plus 1 over R2 plus, and so on. And so if we want to calculate this out for our little 24 ohm and 8 ohm circuit, what you're looking at is 1 over 24 plus 1 over 8 is equal to 4 over 24, which is equal to 1 over 6. 1 over 6 is equal to 1 over the effective resistance. That gives us an effective resistance of 6 ohms. As I said before, our next lesson is going to be taking the Kirchhoff's voltage law and show how we can use it to read the position of a joystick or the position of an on-off push button.